Hi everybody, today we're going to inspect and find out what stack canaries are, or canaries, I don't know how to pronounce it, but this is related to the bird, to the canary bird, oh my god, which was carried down into deep tunnels where mine workers worked, and because there was not enough air down there, and canaries are very sensitive birds, they tended to die when the oxygen levels dropped below a certain threshold, which was an early alarm for humans to indicate that oxygen levels are dropping and you have to leave the tunnel and the mines now. And stack canaries are a similar concept where we have a digital virtual variable in memory, which is our canary. It's a sensitive thing and it alerts us when someone tries to perform a buffer overflow in our program. Now, I'm not an expert in that, but we're going to have a look at the concept together, and I find it quite interesting, and I was pointed at it from you guys in the comments, because in my recent video on Stack Overflow exploits, two of you commented with the stack canary, and both of you mentioned the canary, and I had no idea what that is, so I had to look it up, and I was surprised that I didn't know that concept yet. So let's go into the projects directory and code a simple C source file that we can exploit using a buffer overflow, and then we're going to try to exploit it, and then we're going to add that protection. So this is the projects directory. Let's create a new directory, canary, and let's cd into that. And now let's create a file, vim canary.c. And wait, before my key presses are too loud, let me just put that mat below my keyboard. Okay, now we're ready to code. So let's include standard.io.h, and let's create a main method and keep it very, very simple. We just want to code some minimum code that we need to experiment with the concept. So we have a main method, and inside that main method we are reading something into a variable, for example a uint 32. We need 32 bits of data, 4 bytes, and this is our message. And it's important that this is just a 32-bit message because we want to overflow it. So this is our message, and it is currently empty with, it's just empty. We don't give it any value. And then what is this even complaining about? Use of undeclared identifier message. uint32t. I think that's correct, isn't it? And let's go into the projects directory in the bottom right pane, or here, maybe that's better to read. And let's try to compile it and see if we even compile it properly. Okay, it seems that the type that I'm using is unknown. Probably it's in standard lib, so let's just guess. No. Is it uint32? Oh god. The first line of code and I'm already looking things up online. So uint32t, it exists. which header is it? Standard, C standard int. Does it come from there? C standard int? I don't know. C standard int. But that's not found. No. Something's odd. I'm messing up something. Where is uint32 defined? Standard standard int. Standard int.h. Okay, now this is the variable. I'm never using that variable, and that's why I didn't know that. And then we can scanf something into that variable. And for those who do not know, let's have a look at the man page of scanf. And scanf is a family of functions. The scanf family of functions scans input according to a format as described below, and it's writing that into memory, whatever is scanned into. So we have the scanf function here. It takes as input a format string and then writes that into a variable that is passed here. And these variable argument lists that I used here should be pointers to some memory as far as I remember. Yeah. At least this is saying that the variable arguments lists, blah, 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 are, wait, there was some pointers somewhere. Reads input from the stream pointer, stream, using a variable argument list of pointers. That's the case for vf-scanf, but that's just the explicit variant with the variable arguments list. Yeah, okay. Anyways, we're reading something into memory. And we're reading into memory a number. And we're reading into memory a string. We're reading into memory a string, and that string is going to be passed into the message. Now, because our string is written into message, and message is just 4 bytes, that means our string can just be 4 characters at most, because 1 character is 1 byte. All right, let's try to compile and see what the compiler says. And let's ideally also enable all the warnings and debug flags. And as you can see, the format expects argument of type character pointer, but the argument 2 has type uint32. I think we can work around that by casting this to a character pointer, even though it's not. And then something is written into the message, and then we can do printf message. The provided message is, and then let's print the message to the screen. Message. I think this should be fine. Maybe we would need to cast this to a character pointer here as well. I'm not sure. Character pointer address. Yeah, let's do it like this. So this way the U in 32 here mimics a string. And now it's compiling without warning and everything looks fine. And now it would be expecting that we can write something into the program, and then the program prints out this string with our 4 bytes of a message. So let's try that. Canary, and it waits for user input 1, 2, 3, 4, and the provided message is 1, 2, 3, 4. So we are effectively utilizing this 32-bit integer as a container for our string. All right, now what's important is that, or the key and the core issue with this code is that scanf will scan any message into this variable here, even if it does not fit that size. So if I provide a message that is longer, let's say 1, 2, 3, 4, 5, 6, then as you can see, we get an overflow and stack smashing is detected. That means that the message has overflown into somewhere. Now, let's say we create a variable after the 32-bit message, and that is our empty variable. Let's call it empty variable, just to be clear. So this is expected to be empty. Then we scan data into the message, and then we print something to the console. So let's compile this. Of course, it complains about the empty variable being unused. Well, let's use it. And let's say we give the empty variable a value. For example, I don't know, we also need the null terminating character at the end, I think. So the empty variable has, let's give it the value, let's give it the value canna. Ah, no, that's boring. Beef, let's give it the value beef. No, that doesn't work. We can give it a hexadecimal value because it's a integer. If we gave it a string value, then this would be a pointer to a string, which wouldn't work for our example, I think. So empty variable is set but not used. It's set here but not used. Okay, let's ignore that error message. But what we now can do is we can execute the canary binary and input data. And as you can see, the provided message is 1, 2, 3, 4. And if we overflow by a couple of characters here, as you can see, now it prints out the provided message is 1, 2, 3, 4, 5, 6, but the message doesn't fit into the message variable because this is just 4 bytes. So where are the 5 and 6 stored? Obviously, well, or not obviously, I don't know if it's obvious. The data is written into message, and anything beyond that is just written into the next empty variable here, which is not supposed to be written to. And we can probably confirm that in a debugger. Let's hop into GEB and let's go into the canary project, canary, and then GDB and canary. Let's go. GDB canary layout. Next. This is the assembly code, by the way. I don't know if we can see anything useful here. Yeah, there's our beef variable, which is the right here. This is the value that the empty variable contains, and it's written into I think into this RBP thing register. No, the assembler code is not useful now. We need a memory layout actually to really showcase what's happening. Right, let's go into the next layout where the source code is available. Here it is. This is way better for my purposes. So let's put a breakpoint in line 8 and let's run the program. Now we have a message, print message. It's currently empty. Well, it has a value, but that value is meaningless. And we have the empty variable. Let's see what the value, which value it has, and it's 0. All right, and then we give the empty variable a value 0x beef, which is just an integer value. And let's print the empty variable. And as you can see, it now has some changed value here. And the message is still unchanged. Now we scan a message into the message integer here. Print message, nothing changed. Let's hit next. Now it's waiting for user input. So 1, 2, 3, 4. And let's refresh the layout so everything is cleaned up. Sometimes when you mix up standard input and output and the GDB terminal, then the terminal breaks and we have to refresh this ourselves. Anyway, so now we can print the value of message, and as you can see, there's now a message. So this is the message value, which looks suspiciously large, possibly because we have it can only hold 1, 2, 3, and then it needs to attach the 0 terminating character. So this is even reading beyond the message already. Okay, let's try again. So we put a breakpoint in line 13. Now we run the program. Now if I type 1, 2, 3, then we reach the breakpoint. Let's refresh and let's print the empty variable, which should have this unchanged beef value, which corresponds to that. Just note that this is hexadecimal and this is decimal. That's why they are different. And let's print the message, and the message is this. Does that make sense? No, that doesn't work. But it seems to be the correct value, maybe because this, no idea. Okay, but message contains a value, And if I do print and I print the character pointer, let me just try to print out this exact thing that is being done here. Character pointer, address of message. Ah, okay, that worked. So here we can confirm that the message, that the address of message contains, if it's translated to a string, the string 123. Perfect. Now let's quit this, or let's keep running this, or run from scratch again. Wait, next. Where's the source code? It's gone. Okay, so now let's override the buffer, or let's overflow the buffer by providing a message that is too long. Let's put a breakpoint in line 13 again. Let's run. And now it's querying for standard input, and let's write into it 1, 2, 3, 4, 5, 6. And then let's print the character pointer message. And as you can see, message now contains the string 1, 2, 3, 4, 5, 6, but it is impossible to hold that in the memory only in that variable message. That's because this is reading beyond message. And we can show that by now also printing to console the string that is contained at the address of empty variable. And as you can see, it contains 5, 6. So 4 characters. The 4 characters are stored in message. The first 4 characters are stored in message. And the characters 5 and 6, they overflow into the next variable, 5, 6. And this is basically what a buffer overflow does. It writes data into some other variable where it is not expected. And thus you can exploit things. Now let's also print out the value of the empty variable. Well, let's keep it short. Empty variable and input message. And then let's print the empty variable here. And this should save us some time when debugging. So when we compile the program and execute it, it's now waiting for user input. For example, elephant. And as you can see, the input message is elephant, but the first 4 characters already fill up the input variable. And because there's no 0 terminating character, the printf keeps reading until the first 0 terminating character is encountered. That's why the full elephant is printed here, even though it's not coming from a single variable. It's just coming from the starting address until the 0 terminating character is encountered. And the second empty variable, the variable which we expect empty, it contains hand, even though it should contain a completely different string. So what does our canary now do? How do we take it into the minds of the buffer overflow? Into the dark minds of the buffer overflow. And how do we bring it down there, cage it up, such that it can die when a buffer overflow attack happens. Just like the mine canary. It's quite a simple concept, and that is the following. Let's say we want to protect the empty variable, and let's give it a value that is just 0. Okay, this way we can more easily confirm that when we input something valid, that the input message is this and the empty variable is this. It's 0. If we input something too long, then this went even beyond the empty variable. That's why the stack was smashed, because it was written beyond the stack. So we can write something that fits both variables, and as you can see, this now writes into the empty variable here. Now, let's say the empty variable is our important variable, which we don't want to have manipulated. We want to protect this at all costs. This could be a password, some key, something that's somehow important that we don't want to have manipulated. Well, what we could do is we could introduce a canary inside this right here, canary. Or it could even be a simple character. It doesn't matter. The data type doesn't matter. So this is our canary. And the canary has some value. For example, the canary has the value dead. No, but this is a very bad choice metaphorically, because the canary is actually alive, and only when a buffer overflow happens it's supposed to be dead. So let's put a value of ff. Okay, so that's 4 bytes. 1, 2, 3, 4. 4 bytes. No, we have a character, so we can only have 1 byte of data. So let's say ff is just our single byte. Now, we have the message variable, we have the canary, we have the empty variable. The empty variable is empty. It just contains a couple of zeros. Then the message is scanned. And after the message is scanned and a buffer overflow could have happened at this point, we do the following. We check the status of the canary. And the canary has the value. If the canary has the value ff, then we assume that printf, or well, let's say if the value is not 0xff, that means a buffer overflow has happened. And let's print that to the console. Buffer overflow detected. And then we just exit the application with an error code. So we scan data into the message, and only the message can be overflown, because that's the only point where the user actually enters any data. And before overflowing into the empty variable, the data has to overflow into the canary. And if the data is overflown into the canary, then that means that means that the value has likely changed, and it means that a buffer overflow has been detected. So, and that's how you should be able to protect against a buffer overflow at the most basic level. And let's test that. Let's compile and execute the canary. By the way, what is the pronunciation of canary? I don't want to consistently mispronounce it. Canary. So let's go into a dictionary. There it is. And let's hear.
Canary.
Canary. Is it canary? Cambridge Dictionary for proper English.
Canary.
Canary?
Canary.
Canary. And I said canary.
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 Canary. Well, okay, the canary. All right, I hope I didn't trip any one of you out by saying canary all the time. So let's start the canary, which we already did here, and let's input some user data. For example, zoo zebra, enter, and a buffer overflow was detected. Why? Because the value of the canary was overwritten. If we don't overflow the buffer, for example, by typing just zebra, because we can input 4 characters, but not more. Wait, why is the buffer overflow detected now? It's probably adding the 0 terminating character at the end. So we have to do No? Okay, something is wrong with the code. The canary has the value 0xff, and here we are checking if what's wrong here? I think it's time for some debugging again. Layout next, and then let's go into line 16, run. Oh no, let's breakpoint. Let's put a breakpoint in line 12. Let's run. Now the canary has the value print canary -1. Is 0xff not a valid character? Maybe I just accidentally used this only character, the only value that is not a valid character. I don't know. Let's do 0xfa for comparison. Breakpoint in line 12, and let's run. And the value of canary is, why is it -1? I assigned the value here. I didn't compile. I need to compile. cc canary. Let's do it in this console here. So now it's compiled. Now we can jump into GDB layout next. Breakpoint in line 12, run. And the value of canary is -6. Yeah, but okay, so -1 was a valid value, I think. It's just interpreting the character as a signed value for whatever reason. Print. Okay. Anyways, let's scanf something into the message. And then let's write just the string 1, 2, 3. Now we can print out the character pointer at the address of message, which is 1, 2, 3. So the value stored here is valid. And now let's print the canary. It's still -6. Am I stupid? I think I'm stupid. I have no idea why it's not working. Canary. This is the canary. And the canary is 0xFA. And we assigned 0xFA up here and haven't changed the variable. Does it work if we give it just simply a character value for whatever reason? Let's just write the character X here. And let's compare it with the value X. So this is a character value. It was even complaining about something before. There's a warning here. Why didn't I see this warning when compiling here? Result of comparison. Out of range compare. C compiler enable all warnings. How can I turn on literally all of GCC's warnings? You can't. Maybe W extra. W extra. Ah, there it is. Comparison is always true due to limited range of data type. Okay, so I should have listened or should have inspected the warning before instead of wasting time here. So comparison is always true due to limited range of data type. Doesn't a character hold a single byte, and that right here is a single byte? Or that seems to work. I think it has to do with the fact that this is a signed character, and only unsigned characters can go up to 0xFF. Yeah, that seems to be the case. Okay, I think we got it. So let's quit and do the following. Let's compile this. Now it's working, and the canary is now 0xFF. And now if we don't overflow the buffer, for example by typing 1, 2, 3, 4, 1, 2, 3, 4, nothing happens, and the empty variable is still empty, which is good, which is what we want. We want to protect the empty variable. Well, let's make it even better. Let's make it even better. We want to make this empty variable, we want to make it not an empty variable, we want to make it a holy string. So let's make it a constant character pointer or just a character pointer because I want to technically allow it to be modified, but it shouldn't be modified. Character pointer holy string. This string shall, or this message shall never be changed. So this is our message that we want to protect. Okay, and now we write something here, for example, zoo with 3 O's, and that's the input message. And why didn't it print the holy string down here? Holy string. The holy string is considered empty. Why is that? It's probably because this is allocated somewhere else. Yeah, so this is a bad example. Let's do the following. The holy string is a uint32t, and then this is the following string. This is just const. Let's just name it holy. 4 characters, holy. Okay, I want to write this directly into the stack memory. To do that, I have to convert hex to ASCII somehow. Oh god, what a bloated site. Hexadecimal value string ASCII texts. Okay, ASCII text value holy convert. That's our hexadecimal value. I think we might have to reverse it, but let's try first. Canary 1, 2, 3, 4. Empty variable. Okay. Seems to be not working. Maybe I need to reverse the endianness here. So 5, 9, 4, C, 4, F, 4, 8. Am I stupid? I'm writing something into this. This is a string. And I probably can't. I think I'm confusing addresses and the actual values in memory. So here we have the message, 4-byte integer. We write a string into the address of that message, which is a stack address. So yeah, we should be writing that value into the stack. And then we have the canary variable here. And this is our holy string, which we never want to modify. And it's 0x59 for C, for F, for 8. Let me just confirm this on a different site. Holy. This 4, 8, 4F, 4C, 5, 9, 5, 9. And now we are printing the message down here and the holy string down here. I don't see an issue with that code actually. What if I overflow it? Huh? I overflow it by 2 bytes. And those 2 bytes are printed in the holy variable, which is, but there's a single byte between those, so it can't just overflow into the message, can it? Or do we have this, or because this is a constant string now, or a constant character, maybe the constant character is stored somewhere where I didn't expect it. Object dump, let's check the object dump. Object dump S, canary. And let's pipe that into less. There's our row data section, which contains all the constants, the global constants. I think this might contain the FF if I mess this code up. But I don't see any FF. No. And this is the text section, which contains the... there it is, the holy message. So it is there. So it seems that this holy string is really allocated, and it's allocated after... I don't know what to do with this stuff here. This is assembly instructions, I think. Why does the holy variable have no value? There's a value. It's just not printed somehow. the holy string does have a value. Ah, okay, I know why. So what happens is this message can carry just the message can carry just 4 bytes. If we write a 4-character string into the message, then invisibly the 5th character will be a 0 terminating character, which makes this message overflow into the canary technically. But in that case, I don't get why the canary is not triggering here. So let's debug that. I would expect, because the buffer overflows, that the canary triggers or is triggered. So let's print the canary. It has the value 255, which seems correct. But it's not triggered somehow. And that can only happen if the canary in the memory, in the assembled code, is in a different location than I would expect it to be. Maybe we shouldn't make this a character. Maybe something is messing with or is rearranging the variables in memory. So let's make this a UN32 as well, and let's see if I now overflow this. No, somehow the canary isn't triggered. Why is this not triggered? If I overflow the message, the canary should be changed, which means that this condition should be triggered, and this means that the overflow should be detected. So this is our main method right here. Here we are scanning, we are calling the scanf function. And where is our canary? I wish I understood assembler better. Where is our canary? I think there it is. This is the value 0xff, and we're moving it into, I think this is the base pointer, minus, so offset by some number. Which is probably the address of the canary. I think the fundamental issue is that I'm No, I don't know what the fundamental issue is, honestly. Let's say we give this the value of FF, AA, FF, or BB, EE. Let's compile this and execute it. This seems to work somehow. I think I know why. Because we increased the size of the canary, when we wrote 1, 2, 3, 4 into this variable, the first byte that was overflowing was the 0 terminating character here. And because a 0 was written into 0xFF, which is practically the same as 0x00000, etc. FF, it didn't make a change because the 0 character was overwriting a pre-existing 0. And now this is a problem here. I need to update this variable as well. So let's try 1, 2, 3, 4. No, it seems to not work. 1, 2, 3, 4, 5. I can still somehow overflow the variables. Why is the canary not working? Maybe it makes sense to just print the variable, the value of the canary. Canary. I think this was due to a compiler optimization, probably. Because I was assigning that value, that I was defining the canary and giving it a value but never using it in the code, it probably placed the canary somewhere in the global constants because it knew I wasn't using it. But now that I'm printing that canary value here, the compiler decided to keep that variable on the stack because it's used. And now it seems to be working. So let's have a look. I'm compiling the canary and executing it. And now if we type 1, 2, 3, then the input message is 1, 2, 3. The canary is something holy. Is that expected? No, that's not expected. The canary shouldn't be holy. The canary should be this. Probably this is this. Okay, let's do the following. Let's do the following. The canary should be something like just a buffer of zeros for now. Let's try again. So if I type 1, 2, 3, the input message is 1, 2, 3. So this is 1, 2, 3. The canary is nothing because it's just zeros, which makes sense. And the holy variable is protected. It's holy. Now, if I type 1, 2, 3, 4, that should give us the same result, because now the 0 terminating character is overflowing into the canary, but it's not changing the canary because it's all zeros. So this is fine, or appears to be fine, although it's technically not fine. And let's try to overflow it with a 5, so 1 extra character. This is now a buffer overflow, and it detects the buffer overflow. So the previous failure to detect the buffer overflow was because the canary was somehow optimized outside of the stack, because it was never called again inside the main method. At least that's my best explanation for now. Okay, but how can we make this better? Because now technically what the user could do is somehow feed stuff here, and then the attacker could overflow the buffer with 1, 2, 3, 4, and then feed those characters also somehow in here. I think that's not possible via regular standard input. You have to somehow write 0 bytes in here, and then they can still overwrite the holy string. But let's try that. I think that's a very valuable experiment. Forward bytes to standard in Linux. How to standard in any byte? Standard in hex or pipe byte to standard in. I know it was possible using Python, but that was not a very pleasant experience. Let me just think for a second. Linux convert ASCII to byte. Yeah, there's the Python function that does this. But is this really the best way? We can make a better example with something that we can do via keyboard easily. For example, we can say that our canary is something that is within the ASCII character space. So let's say it is just CCCCC. CCCC. And that would be 63, 63, 63. Or 63, 63, 63, 63. This means the following. So now we are executing the canary. We are typing something in, and it's... of course, I have to also change the value down here. Bear with me. Let's try again. Okay, now it's working better than before, because the 1, 2, 3, 4 is writing something into the canary, and that is the null terminating character at the end of the 1, 2, 3, 4 string. So we can only write 1, 2, 3 into this, and the input message is 1, 2, 3. The canary is CCCCC without a 0 terminating character at the end, which makes sense. And then it's printing out the rest of the holy variable directly, because there's no 0 termination here. Good, but that is fine. I hope you get this example. So this is the canary, and this is also already the next variable. It's just printed because there's no 0 terminator here. And now we could do the following. We could just write 1, 2, 3, CCCCC. Oh, wait. No, we can write 1, 2, 3, 4, which is filling up the message. Then we can fill up the canary with something that bypasses this, CCCC. And now we can probably manipulate the holy string. And let's call it moly. And as you can see, our canary was not able to protect against that attack that is possible if you know the code. So if you know the code and if you know the canary, then you can still perform a buffer overflow exploit, because you can write something into the message, then you can write something that matches the canary, which we did, and then you can chain it, then you can input anything that writes into the overflow string. So now our holy variable, which was so holy that we wanted to protect it at all costs, is modified. Damn it. Let's try again. 1, 2, 3, or 1, 2, 3, 4. 1, 2, 3, 4. And let's write something dump. And now our holy variable is dump. How unfortunate is that? Yeah, that's exactly what we don't want. Now, how can we protect our holy variable using a canary? If we can just do this right here. And luckily there's still a solution, and that is the following, and modern day canaries do that. And that is, we can just give the canary a random value. So let's do that. Let's create a random value. Maybe, yeah, I'll use a random value from standard lib random, probably. Yeah. Or even better, urandom. That would come from Linux random, and we could use, or we can just read in from this. No, we have to do it properly. We need to use srandom and give it a seed. What is a proper seed? Is there an example here? No, but we can still try. So let's include standard lib. It's already included. And the point is that if we give the canary a random value that is generated at runtime, then the attacker has a much harder time finding out what the canary is. And basically for each execution of the binary of the program, the attacker has to know the randomly generated canary, which makes it much harder to buffer overflow attack. So let's generate a random canary. Or first let's create a seed. Seed random. And we can use srand time null. Sounds good. It's good enough for basic general use. Okay, so that uses the current time as a seed. srand. But this function was called srandom. Wait, what is srand? Rand, srand. They use the same random number generator as random and srandom. So it's just the same thing, probably. srand time null. And that is our random canary. Now, if we do, Well, what does this return even? I already forgot. This returns a void. This is just the initializer. Okay. Okay. So this initializes the seed for the random number generator. And then after that, we can just use random as regularly, I think. But I like this more. Okay, so we do the following. We call srand time null, then random to generate our uint32t random number. And this is a random number, and then the canary is the random number, gets the random number. And I think I have to probably include time.h to resolve this function right here. And where is random coming from? Random should be coming from standard lib.h, which we already included. And we need to cast this to a uint32. Currently it's outputting a long, but this is needed to make it compatible. Okay, now we have created our own super canary. It's basically like instead of taking the same bird down into the tunnels and the mines every time, and an evil attacker knows which gas this bird is not susceptible to and will survive, such that the attacker can pump that gas into the mines and kill us. Instead of taking that same bird every time, we just take a different bird every time. And the attacker never knows which gas this canary is, well, not susceptible to, or susceptible to? Well, the attacker just doesn't know the bird. Let's put it like this. The attacker doesn't know the bird, and therefore there's a very, 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 very incredibly high chance that the bird will die for pretty much any gas that the attacker pumps into the mines. Okay, now what we do here is we compile and execute the program down here. We write something here. And now, how do we overflow the canary? No idea. Let's try cc, cc, cc. I mean cc, cc. And let's try to overwrite the holy variable with moly again. And it detected a buffer overflow. And now this is very, very hard to hack. This is how the protection works. Because the canary is now a random number. As you can see, if we execute the program regularly, so this is not regularly, this is also already buffer overflowing, let's say 1, 2, 3, then we get an output of the canary here. I don't know why the holy has this roof character appended. Is the canary now put after holy somehow? Canary is this, holy, and then this. I think the long that is returned by the random is too big. Probably we have to do this. Long, and the canary is now also a long. Maybe the long is a 64-bit number on my system. No, why is the canary placed after this? Random number. The canary gets the value of a random number. We probably have to print it as a digit, as a long now. Wait, no. Long digit canary. Maybe the formatting was just messed up. That's fine. The canary is a random number and the holy variable is now holy fuck. What a coincidence. I don't get why is this fk appended to the holy variable now? This is the holy string. We don't want to modify it. Should we? Maybe the issue is just that it doesn't have a terminating 0 character and then whatever is printed from the stack. I don't know. There's too little control going on inside this code here. Too little good practices. Now the 0 terminating character is at the beginning. Should probably do this. Or even, what happens if we just prepend it? No. Yeah, now it seems to be working, but I'm not very happy that this is acting the way it does. Maybe we should have a uint or even a character array, holy string, and it's just holy. Why didn't I do this in the beginning? Just a character array. Why didn't I do this in the beginning? Because now this is a character array with 5 entries, and the last one is the 0 terminator. Let's see. Yeah, and that seems to be working. Okay. Oh my god. There were so many stupid programming issues in this episode. I hope you excuse them. Implicit declaration. What is that? But it's not printing any warning in the bottom right terminal. Anyways, okay. Now, what's going on here? What's going on in our final product? I will wrap up the video now because now it's working. We have created a small program, a very, very basic program that contains buffer overflow protection. We have a variable, the input message, which we can write into 3 characters and a 0 terminating character. After that, anything beyond that will overflow into the so-called canary, which is now a random number. And if the canary is not the random generated number anymore, which means it changed, then that means that the message, the input into the message has overflown and a buffer overflow is detected. This means we can now write anything into the input as long as it is contained within that message. It will act nicely. The binary will act nicely. The canary will have some value that should never be changed, that can never be changed. And the canary is guiding our holy variable, which resides in memory in the stack after this random number. But if the random number is ever changed because the input overflows, then the canary is triggered and the program exits before anything is done with those important holy variables, with that important holy variable. So now when we overflow the buffer, for example, by typing 4 characters instead of 3, we have tripped the buffer overflow detected message and the program has exited. Now, of course, this way of protecting the buffer in this example looks incredibly stupid, because we could have broken this down to a simple numbers of character checks somehow. No, we couldn't have, because we scan things into the message and the scanf function will write stuff regardless of how many characters you type until the new line or until some terminating end. I don't know. But there's no way to really protect this with the number of characters input. Because first you input stuff and then you can only count the number of characters that was input or that were input. So that's a futile effort. Yeah, okay, let's wrap this up. I've learned a new concept thanks to you guys. I don't even know if I applied it correctly, but if you also learned something and like this video learning a bit about buffer overflow protection using canaries, those little canaries, then stick around and see you next time. Bye.